Okay, everyone. Thank you guys for joining. I think you all heard, but this meeting is being recorded. So just a little housekeeping stuff here. Meeting's being recorded. If you have any questions, please raise your hand and we will do our best to get to you in the chat. So welcome you all. This is an exciting time. Welcome to the webinar of Unengineering Medical Devices. This is chapter 1 of a 6-part series that we're putting together here at Wipro. And today we are going to be talking about shadow mode. I'm Michael Ward. I'm going to be your host today. We're thrilled to have you guys join us for this exciting session where we're going to explore how traditional engineering approaches are being reimagined to meet the evolving demands of medical device innovation. Joining me today is our featured speaker, Thomas Mueller. He is the Vice President and CTO for Wipro's engineering practice. With deep expertise in digital transformation and product innovation, Thomas will guide us through the concept of shadow mode and its implications for the future of medical device technology. Thomas, if you want to go to the agenda slide here. So just a little bit on the agenda today, guys. This is what we're going to be covering: how to unengineer medical devices. We're going to get into shadow mode. We're going to talk about adaptive devices that can learn from the best. We're going to talk about reframing innovation as a continuous adaptive process, how to safely deploy tomorrow's innovations today, and how to accelerate innovation without eroding trust. And then we're going to get into a little bit about what Wipro is doing with CloudCareAl and how that fits into all of this. So without further ado, Thomas, it's your show. Handing it off to you, man.
Thanks, Michael, and good morning, good afternoon, everyone. Thanks for joining, and excited to share with you the first chapter in our unengineering story on MedTech. You may ask, why do you call it like this? There's a simple reason. We simply believe we need to rethink how the technology in healthcare, particularly in the device space, has been brought together, has been architected, and about the vectors and the speed of change that we propose. This is supposed to take. This is not decoupled from real world demand. This is based on the work that we do with our customers for many, many decades. Some of you may not know that Wipro is deeply invested in the healthcare sector, dating back about 35 years when our founder, Azim Bremji, who turned just 80 this weekend, entered a joint venture in India with GE Healthcare to manufacture tailored imaging devices for the fast and rapid growing Indian healthcare market. So we've been, as a company, on this journey for a very long time. Historically, also, Wipro was a hardware manufacturer in the computer space back in the 80s and 90s, before we turned into a services company, a global powerhouse. And I believe it's really important, to see that this is anchored in, decades of real world experience. And in recent years, obviously, we took a lot of influence from other industries that we're working for that have gone through major disruptions. The telecommunication space is one of such areas, and automotive, which I will talk a little later. Just for my short introduction, I'm Thomas Mueller. I'm based in Colorado. I lead Wipro's engineering chief technology officer office, and that spans across our practices, developing chips, silicon design, chip validation, all the way through hardware designs, embedded hardware, large-scale AI data center hardware that spans the software that drives this hardware, the embedded software, the application software, and all the way includes also vertical practices such as Industry 4.0 with our IoT arm, our automotive engineering, our network product engineering. So we are together today about 22,000 engineers here in Wipro that specifically help product development organizations create basically product that get better every day. If we look into what is setting the tone, we all are used to wake up with basically news every day that can, plot the path where, some of our industries are going. And particularly after COVID, some industries have seen very disruptive moments of technology change and advances. We all remember the arrival of AI back in late 2022. And ever since, obviously, many
Thomas, sorry to Sorry to stop you for a second. You're cutting in and out a little bit. Maybe go off video so we can get some bandwidth freed up.
Shouldn't be. Let me try to change this here.
It wasn't too bad, but there were 2 occasions that you dropped off for a second. So I just want to make sure we're not losing you and we're getting all the good information here. And sorry, attendees, I do not have any jokes prepared for technical difficulties like this. So we're just going to have to ride through the silence.
Well, we could talk about a disruption in the video conferencing markets and the bridge that we're using.
There you go. Okay, we can hear you. We can hear you clearly now, Thomas.
Okay, let me just wrap this up here. Sorry, I'll switch my tech settings here. Perhaps that is gonna help with that. So setting the tone. Innovation traditionally had very long innovation cycles, especially in the product devices side. We're talking about years. Sometimes platforms were multi-year projects, 3 to 5 years. Some of the larger platforms of products were, into the 3 digits of $1 million investments to develop the underlying platforms. Every industry, and this is not particularly to the medical device industry, has tightened regulatory constraints that are individually by geography. The US market obviously is one of the largest, to have that regulatory pressure. And the approval cycles, have historically been fairly long because humans involved into this. There's a lot of data points needed. The safety is absolutely imperative. And this is something that this industry particularly has common with many other industries, such as the mobility services sector, such as the aviation sector. Banking is not so much about people safety, but it's about the security and trust. And there is clearly expectations around care. We all expect care to be basically available to everyone in ways that it is accessible, technically accessible 24/7, that it is financially accessible, and also accessible in locations, for example, and for demographies of varying age. And the technology has tremendously helped, especially in times of COVID, where patient care was moved to telemedicine solutions to really expand that use. And today's sensors have become more and more sophisticated. I believe every person today that is using a smartphone is already wearing a set of about 20 to 30 key sensors. Wearables like watches have become health devices that are fairly sophisticated, including ECG functions and others that are, helping really to diagnose critical conditions a lot earlier in the cycle. But cost management is really one of the challenges. If I look into the current, situation that I live here in the United States, I get transparent bills about the cost of treatments, but these costs are shockingly high, and the money that circulates in the system is really, really enormous, and something that is really to be considered as this spend has only one direction: it goes up. Skill challenges are plaguing our industry historically for a long time. It's in the area of creating the devices, which span from very sophisticated silicon chips that can empower innovations in wearable devices, in implants, for example, to the robotic solutions. It requires continuously evolving skill sets. AI first skill sets have not been, anything new to us. We've been, on this journey for many, many years since computer vision started in the 2010 years. But today's landscape of devices is extremely fragmented. And I can compare this probably to the industrial manufacturing sector, where we have a huge amount of very specific devices. Most of them are connected today, internet connected or locally connected to environments of manufacturing. But the situation in medical devices is also that many of those devices, due to their extreme complex engineering and maintenance cycles, are fairly expensive. Most doctors' offices can only afford to buy one radiology device in 2 decades or so, and not able to upgrade this. Whenever I visit my dentist, for example, and take a look at his probably 1980
X-ray solution. It reminds me of that, and the conversation is clearly, I cannot afford, to refresh this device. I still need to use it, but that cuts, that particular treatment center out from innovations. And innovation needs are evolving rapidly as we have ways to diagnose critical conditions a lot earlier. But that is in contrast to the long development cycles that these solutions typically need. So there's a lot of potential to really address this, and it comes in times of uncertainty. We've seen all that the global markets have been, shaken up by basically weekly, monthly, tariff decisions. Manufacturing allocations need to be changed. So we believe this is absolutely the time now to really rethink how can we unengineer many of the constraints that this industry have been there. And we're not doing this out of the blue. We're doing this because we've done it in other industries successfully before. And the industries that I'm going to walk you through that have done this before successfully are telecommunications products and automotive. So what is really driving us? And what's driving us is back to many conversations we had with clients, which boil down to a simple vision. The question is, can we actually engineer devices that are getting better basically every day, that add new capabilities, that get better, that get refined every single day through its use? And in other words, you can say these devices are contributing devices. They're contributing to the user that uses that device, they're contributing to the patient, and they're contributing also to its maker, the company that has created that particular device. It gets a value in return. And you would say, hang on, how does this really work in a real world? Well, I give you a simple example. Anyone that operates a Tesla vehicle in the real world today is helping its maker, Tesla, to actually create a better product. And he does that for free. Basically, driving around the block with my Tesla here in the US is helping Tesla to create better software that is more human-like, it assimilates the human baseline a lot better. It's a very valuable contribution. And believe it or not, no other car maker today, no other car maker has that ability in its product on the same scalable basis to contribute. So in other words, other car makers today are producing non-contributing products. And this is a question that we really need to ask here. And this is fundamental for chapter 1 in the unengineering playbook of Wipro Engineering, is you need to ask yourself the question, is the product that my company creates really helping me to create better products tomorrow, in the next months, in the next year? Are they contributing? And if the answer is no, they're not contributing, then this is an entry point for really reconsidering this and to really unravel some of the capabilities that come with unengineering of medical devices. Sorry, I have to move something out of my screen here. Looking at the MedTech sector, while it is moving fast, many devices are stuck in the past. Practical example for that. MedTech is definitely moving fast. We've seen innovations that come out of countries like China at extremely high pace. And these devices are small, inexpensive consumerized devices with amazing sensoric capabilities. But we also have medical devices, for example, in the imaging sector, that have been innovated within the last years at extremely high speed. And in other industries, I'll come to that example later on, we've seen similar developments. The flexibility that is needed to change fast is not, typically the external hardware. It's not the form factor, but it's what's inside. It is the capabilities that sit inside the product. Sensor technology is not evolving rapidly. Sensor technology is often complex. Diagnostic, like PET scans, for example, is evolving, at a certain pace that is certainly decoupled from the electronics control systems, from the software capabilities that are coming out of this. So the sensor platforms and the actuation platforms evolve at a different speed. but the software that really drives them and the underlying hardware also that enables the software to strive is evolving at rapid speeds. Every year we see a new generation of silicon, for example, arriving in consumerized devices. We are used to our smartphones, are getting a chip that is maybe 20, 30% faster than the previous generation, and it's more efficient because it's been produced with a new manufacturing process that moves to a lower node, with an increased density of transistors on that capacity, and that improves the power cycle, that improves the battery life and the performance, and reduces the cooling and heating envelopes. So the hardware advances typically in cycles that are in sometimes less than 1 year, sometimes 2 years or 3 years, and these are rapid. And at the same point, also the price points are dropping. That's really important to understand, is the price points in high performance compute hardware have been significantly dropping. Moore's law, as you're familiar with this, is applicable to typically the standard compute architectures, but is not reflected in the medical devices and its underlying computerized control system, the electronic architecture that powers those devices, whether it's a small toothbrush that is electric, whether it's a wearable implant, or whether it's a full-fledged room-size radiology machine. We're not seeing that the hardware speed is actually translated into product development speed. And digital first is obviously a given these days, but the hardware capacity limitations is often the reason not to go above and beyond what the device is actually capable of doing. So if we take this as an opportunity, the question is, how do we unengineer really a device? In the first chapter we're looking in today, it starts really to create a modular software-defined platform. And by modularity, what we're meaning is the ability to upgrade hardware independent from the need to upgrade software. We said, how is this possible? Well, it's possible because we're doing this in data centers for the last 15 plus years. Thanks to innovations of hardware abstraction, virtualization, multi-tenant architectures in hardware, we've been able to basically evolve data center hardware at a different speed than the software that is actually sitting in enterprise data centers. So a software-defined data center, which has been around for the last 15 years at least, and sits underneath every hyperscaler cloud today, is a fundamental principle of disaggregation. And this fundamental principle of disaggregation is really what allows us to do this. You say, is it more expensive? No, actually it isn't. It is using the same compute hardware, the same networking, the same storage that we're using today. That applies to every single device. So abstraction and disaggregation is really the starting point. And that way we can future-proof devices, not limited by its form factor. We can actually really have a modular design and reuse the underlying underlying hardware cycle that evolves in a certain speed, but the software cycle, the software that sits on top, is today often created in a very monolithic way. Monolithic, what I mean by this is we're using millions of lines of code that sit in products itself, and of course the amount of software that sits offboard of the product. It sits in an edge cloud. That could be in a hospital environment. It could be in a public cloud, in a private cloud. It doesn't depend on. But where we're getting to is that shadow mode is really the capability that we're adding to this construct, and shadow mode comes at a very insignificant cost to the device. It basically uses an extra sandbox, and I'm going to come to some technicalities. It uses an extra sandbox on the device itself that is exposed in real time to the same sensor and actuation components that are constituting the product. Remember, I'm talking about small wearable implant type of devices, all the way to room filling radiology machines here potentially. And how do we look at this from a strategic standpoint? You say shadow mode, has it been around anywhere? Yep, I mentioned the example before. It's been used in products like a Tesla vehicle. It's been used in telecommunication products quite widely. Why are we proposing it to do it right here? Well, first of all, signals need to be processed at the source of ingress. And at the source of ingress is typically the device itself. So we can innovate closer to the device. And why is it such a benefit? Well, we can actually learn in real time in a safe environment, we can pilot new functions in a live environment against the real world signals. We're not, doing synthetic data. We're not creating basically virtual worlds per se that simulate this or emulate anything. We're actually using real world data in these shadow modes, and we can learn from these data in real time. On the flip side, we can also in real time decide which data is valuable and which is not. So we're not collecting haystacks. We're able to collect needles instead of haystacks. What does it help us with? It helps us significantly reduce the cost of waste. Every amount of megabyte, every gigabyte of data that you're ingesting into a cloud platform causes long-term cost and is unlikely to be reduced. It's just growing. So the cloud cost is a significant contribution to the high cost of the compute overall in healthcare and the devices in function. If the largest, autonomous company or a robotic company, Tesla, is using their own private cloud, it's for a reason. It is because they have now the ability to optimize their cost and capability metrics on their own instead of relying on a public cloud partner. And then fundamentally, shadow mode is about safety. It is about running a software in a live environment to be able to see its performance in real life before it impacts the safety and the performance of the product. In other words, is before you are releasing it. And this is a really important capability. And of course, we're collecting real world evidence. We're not just using synthetic data that is assumed to be close to real. We're actually using it in real. So we can see the performance against real world patient data, real world clinical and life science data. So it's a huge new capability. Has it been used before? I mentioned an example. In the automotive industry, the way that the path to autonomy, the path to services like robotaxi services has been plotted is a path that requires an unimaginable amount of real world data validation against millions and tens of millions of human behavior patterns. And why is this so complex? Because the world is ever so complex, and coding a real world complexity into algorithmic prescriptive code is hardly possible. An industry that had to learn the hard way that this is not possible is the automotive industry. In the early days of driver assistance technology, back in the 2000 years, engineers created basically algorithms that basically described solutions to a real world singularity complexity problem. And for example, a lane departure assistant or a distance warner or an emergency brake assistance. These were all discrete solutions addressing a potentially incredibly complex problem. And these solutions were point solutions that were not connected and prescriptive. And they caused an enormous amount of false positive events that actually changed the perception of a user from this is an assistance technology that is potentially beneficial to me to a technology that can be quite intrusive, that can be quite annoying and quite irritating and distracting. And why is that so? Because these systems were built in a one-way road. There was no feedback channel. There was no validation if events that led to actions have actually been correlated correctly, and if not, how do we learn from this? So this goes back to the question: how do we learn from its use? The automotive industry is now changing. New products that are being released this year from other OEMs are showing exactly those capabilities they built in. The new Mercedes CLA platform just launched, has those capabilities. A number of Chinese OEMs like Xiaomi, for example, NIO, just to mention a few of those brands that you might have heard, have exactly those capabilities. And Huawei, who is a big propellant behind these technologies and originating in the networking space, is bringing its technology prowess to really drive this process for Chinese OEMs that are technology-wise a lot more advanced than many of their established Western brands. I don't want to call out any names here, but it is clear that the technology path is really led by big tech, new age companies that are really helping here. And we see Google's Waymo experiences on our roads with fantastic robotaxi services expanding now at a much higher pace. So in healthcare, as we don't stand still, how can we really leverage this? And shadow mode is one of those capabilities. We have a basically simplistic drawing here as a box diagram. And what you can see is that while infrastructure, actuators, and sensors and hardware remain in principle unchanged, you can do this with a single processor. Virtualization is the abstraction layer that we're adding to this. And the abstraction really gives us a number of new capabilities that includes the shadow mode, basically bubbled in the product. It allows us to release new applications in a pilot environment in live. It allows us to test the pre-production code in live data, which is super important for QARA processes, quality assurance, regulatory affair processes in every geography that I'm familiar with. And we are having the ability to provide functional safety. How do you say functional safety? What does it mean? It means that we can guarantee in this architecture and maximum end-to-end latency. Guaranteed end-to-end latency is the fundamental principle of functional safety. We've been engineering this in the automotive industry now for many, many years, often in discrete ways, but we can now do it in a shared compute and abstracted platform thanks to advances in virtualization. This requires a huge ecosystem, and we've been working with major ecosystem partners on this journey for a very long time to achieve this, especially since our software is now moving from a monolithic to a composable microservices-oriented architecture. We're applying the principles of SOA in the product. You might say, oh, we do SOA already. Yes, you do it presumably often in a edge server that sits in a hospital or a treatment center. You do it in your aggregation server, but you're not doing it in the product itself. Why is this so important? Because it reduces the cost of engineering in your product significantly, because the changes that you're making require only very discrete testing instead of a holistic end-to-end testing of your product. So there's a huge advantage, and we've seen this now in the automotive industry, where we have moved literally 50 to 100 million lines of code with some OEMs into a microservices architecture on embedded platforms distributed across more than 50 discrete ECUs, electronic control units. And we have succeeded in that. And we added high-performance controllers, basically bigger embedded computers based mostly on ARM architecture to this. So the new innovation starts really in the device. It starts on a platform that is fully disaggregated. It creates the sandbox, and the sandbox has multiple use cases to help. It even helps with the product application lifecycle. It helps you to deploy a product ahead of its launch and basically switch to a cutover migration. One of the key benefits we're seeing is that the deployment of an embedded software, it depends on the size of the product, is not going to measure it in hours. It's not measured in half hours. It's actually measured in a boot cycle. And a boot cycle of a device is typically less than 2 minutes. In some instances, less than 30 seconds. So we can cut over the migration times to new software significantly, which improves, of course, the availability and the uptime of the equipment. We can also run this in a passive listener mode to really have detection probes looking for certain anomalies in certain markets with certain structures, certain patients in certain scenarios, to collect relevant data probes to really drive the AI-based insights that we're extracting from this. We don't want to collect the noise. We really want to collect the key events that we're looking for. We can run patient studies at scale with this mechanism at a lot lower cost, at a lot less impact than you would traditionally do this. So it's a zero impact deployment ultimately. And then we're building what we call the real world AI harvester. And this is basically our cyclic AI platform, which starts in a device. It starts in a device with the shadow mode to be able to really continuously extract the relevant information that are ingested into our AI care data universe. The data universe is built either with a single brand partner. It can be built across a chain of partners. Multi-party ecosystem contribution is extremely important, and we're seeing great examples in the oil and gas industry, where we are engaged with partners for a long time in, for example, the open subsurface data universe, where partners successfully share data that are actually competitive in the market to allow for a joint look at key data of an industry that has extremely high cost of generating those data from exploration, geospatial exploration operations. So we're using a fleet of products, and that can be, starting off with a single product. It can go into the tens, the hundreds, the thousands, and the millions of products that are continuously contributing. And those are contributing with real-world validated data. The heart of Shadow Mode is really that we are empowering a cyclic AI platform, which sits at the heart of a continuously improving product fleet. And while we have in our architecture foreseen and proven now that the live app, performs its applications exactly as desired, it has the guaranteed maximum latency of its actions, so it can sense and act in real time. It applies to robotic devices exactly in the same way. So we build robotic control systems for advanced robotics exactly in this way that we're showing here. The Shadow Mode is really the value creator and the booster for a software-defined medical device product that gives us the capabilities. What we are affecting with this is we are able to affect a shorten of regulatory cycles. While humans are still there that have to, prepare this, the preparation of the necessary paperwork, the submission with agentic AI today, we can significantly shorten that. The amount of consultants needed to process this is a significant opportunity for our agentic AI solutions that we build to really shorten these cycles. But it is the message, the content of the data that we create from Shadow Mode that really impacts the regulatory cycles. But the question is, how can you prove that this change is safe? If you can go back through a lineage of data in the real world by exactly showing it is safe to use, we're addressing this challenge in the medical device industry the same way that we're addressing it in the automotive industry by bringing robotaxis on the street, because we can prove to the regulator that the technology, the new software release, is safe to use. And we've been seeing the shift in and stance on autonomous vehicle regulations in markets like China, in Europe, in the US is a very different approach to this. Regulators require different things altogether, different timelines, different amount of data points, different information, different types of proving. But altogether, we've seen that those players with Shadow Mode capabilities have an extreme advantage to shorten those regulatory cycles, which is basically the path to revenue growth ultimately and to a safe product, more importantly. So this is what we are achieving with this. So it's a foundation that enables agility, speed. It increases the safety of the product significantly because we can prove that the software is safe to use at scale before we deploy it. It's more sustainable, obviously. And the strategy that really, sits in this allows us to create also co-creation solution with other innovation partners. We can work with a third party to test their hypothesis on our product or multiple hypotheses at the same time on our product, allowing us to find innovations that work to prove a hypothesis or to falsify it in real time at the scale of a fleet. So ultimately, agility and ultimately also the compliance is a beneficiary downstream from this. Well, this today is basically our first chapter in our unengineering story. We have more chapters to come, so this is a glimpse of what is going to happen in chapters 2 to 6. We're going to speak about the software-defined medical devices and its architecture and how it impacts the industry going forward, how devices are basically to become more scalable. We're talking about the data aspects in more detail. We're showing you exactly examples of agentic AI that are transforming the software development lifecycle that sits behind us. So this is the digital engineering IT, if you will, and how we're going to change this, respectively talking about ALM and PLM here, and how we can create variants or hat designs. Hat means is a term from other industries. How we can create hat designs that are changing customer preferences. And our company's collaboration with GE back in India 35 years ago was exactly one of those examples. So these are the chapters to come. I hope you stay tuned and join us on this journey. Last but not least, I want to give you a short 1-minute introduction to CloudCareAl, which is the software-defined medical device platform that my team here has developed over the course of the past 18 months. And CloudCareAl is exactly our incorporation of a platform that is basically bringing unengineering medical devices to our customers and allows us to co-create with them solutions a lot faster. What we've done in CloudCareAl is we've taken, of course, aspects from cybersecurity, which are, is also a key beneficiary into this. We have the aspect of innovation that is closer to device. We basically leverage AI at the entry point of data, right at the sensor level, when it hits our compute system. It's about reliability of a system, fail-safe operations and updates, no more brick devices in the field. OTA comes inherently with this, and we have very advanced OTA solutions that are, superseding lots of established IoT solutions in this space. Here, we're going to talk about a pilot and live capability that we can showcase you, how we can co-create and learn from the best in the industry, how we improve, for example, perception and sensor fusion, how we can use software-defined sensors that can be augmented through software instead of hardware, which is a very important aspect that we learn from sectors like defense, for example, and automotive. And ultimately, we can scale infinitely. So a product that can stay updated and relevant for at least 10 years or longer is not a vision anymore. It's reality. It's what we built for automotive. It's what we built for the networking industry, the network products industry. And it is something that we're now bringing to the medical device sector. Last but not least, we can migrate to safe and compliant code. We're using 40-plus-year-old coding languages in the embedded space, which is hard to imagine. But C and C++ have been dominating this market at large. And we can change this with our scale AI-based migration to safe coding techniques like Rust, which we are applying across industries right now. And last but not least, also zero-touch provisioning. Device features are based on profiles, based on users. We understand the context and intent, and we can do zero-touch provisioning. So there's a number of key differentiators that we have unengineered with CloudCareAl. My team and I are happy to, dive deeper into this and have a detailed discussion with you around this. So please feel free to reach out for us for a demo, and we're happy to share that with you. Overall, we're all, committed to really drive the efficiency of care providers. We want to improve the quality of patient care overall. That's the key beneficiary, and we want to make a major contribution to the cost reduction across the entire value chain. So medical devices are evolving and incorporate AI at the point of care. That's already happening today, but we're taking it really to the next level, and that's why we, unengineer medical devices chapter by chapter. Today was chapter 1. Thank you for tuning in. Thank you for spending time with us to look at this innovation opportunity. And we hope to be in touch with you at any point in the future, hopefully very soon. Thank you. Michael, over to you.
Great. Thanks so much, Thomas. Thanks, everybody, for joining. We do have 5 minutes here. If anyone on the call has a question, please put that in the chat. If not, we will get off this call in a few minutes, and we will be sending this recording out to everyone that has participated here. So again, thank you all so much. And if you have any questions, please add it into the chat now. We'll stay on for the next 5 minutes. If you are finished here, then have a great rest of your Wednesday. And thanks for joining.